My name is Sumit Diware, and welcome to my presentation titled Hardware-Aware Quantization for Accurate Memristor-Based Neural Networks. So this paper was published in ICCAD 2020. I'll start with a brief introduction myself, although Professor has kindly introduced me, and also thank you, Professor, for having me. So I finished my PhD from TU Delft last year, and for my doctoral work, I received the DATE EDA Thesis Award for 2025. I mainly work on AI processing architectures with the focus in computation in memory and neuromorphic hardware. So the agenda for today's presentation will be that I'll start with a brief introduction of the topic. Then we'll go into some fundamentals of computation in memory, specifically for edge AI. Then I'll introduce the challenges and how related works address them. This will be followed by the quantization methodology that we propose. Then I'll describe the results which validate the methodology, and we'll end with the conclusions. So starting with the introduction, as we know, artificial intelligence basically refers to systems that can perform cognitive tasks which are beyond standard number crunching. Here are a few examples of some products and services that leverage AI for the execution. And as per a recent report from UN Trade and Development, the AI market size is projected to reach almost the size of Germany's economy by 2033. So AI has already become an integral part of our lives, and that share is going to increase more and more as we move forward in the future. So having understood the relevance of AI, let's move on to how the AI computations are carried out in various paradigms. So the most popular paradigm is the cloud AI, where you perform the computations in a data center or a big server, and you just interact with the user devices to get the query and send the results. However, if you move the calculations to the end device, you get several benefits like fast responses, saving the bandwidth costs, better privacy, security, and service reliability. So recently, there has been much more of a paradigm shift towards edge AI. Now, edge AI is good, as we have established. So what happens if you try to use the conventional hardware to build the edge AI solutions? You run into several problems. I have listed the two main problems on this slide. The first problem, of course, is the data transfer bottleneck because of the separation of memory and compute. As you can see, the memory access consumes orders of magnitude more energy than the computations. So that is not ideal for resource-constrained edge devices. And moreover, the memory technologies that are being used like SRAM, DRAM have a high standby energy, leakage, or refresh, and are becoming progressively difficult to scale due to the charge-based storage. So here is a graph showing the leakage in SRAM and its trend with the technology. So to summarize, conventional hardware doesn't seem to be the best option to make the resource-constrained edge AI solutions. This is where computation in memory comes to the rescue. So what is computation in memory? It is basically an emerging paradigm which uses emerging memory devices called memristors to perform in-place computations. So you overcome the data transfer bottleneck, and the memristors are non-volatile, overcoming the issues with the conventional memories. So an example is shown in this figure. So we have two layers of a neural network, a small sample connected by certain weights. If you convert the inputs into voltages and stream them through a grid of conductances which represent these weights, you basically get the output neurons as currents, and by after conversion you get them in digital just by the flow of the data and without all the fetch and compute execution. So this gives you the basic key benefits. It's energy efficiency, as there is no data transfer bottleneck. Memristors are scalable and compact, so your hardware is able to meet the space constraints on edge. And this architecture itself is naturally suited for brain-like computing, because in brain, neurons send excitations through weighted synapses to other sets of neurons, which is exactly what this model is doing. Now, what is shown here is kind of an ideal picture because the resolutions of these data converters are limited and the bit size of the memristor is limited. So in practice, a technique called bit slicing is employed, where you split your inputs in time and split your weights in space to match the resolutions and to keep the ADC resolution in check, and use the post-processing to combine these reverse the effect of these splits basically to recover the full precision outputs. And as the analog computation is very powerful, despite the split, you are still able to reap the benefits of the in-memory computing. Now, a crucial thing is that if you look at this architecture, all these inputs, weights, and the outputs, they have to follow a certain quantized format. So that format gives you better compatibility with the same hardware and also has some other benefits. So let's look into that numeric representation format on the next slide. So that format is actually a fixed point quantization format. So what is happening here is that you are representing your real number, which is a fixed point number, as basically an integer with an implicit scaling factor. So you do the real number processing, but with an integer arithmetic. So it's directly compatible with any standard SIM architecture and also saves energy because all the post processing that happens outside the analog is also on integer operands. So here is just a sample of how the fixed point format looks and how the conversion is carried out. So as for format, the fixed point format is just an integer with a given word length. The only catch is that you have a implicit radix point after a certain designated number of bits that you called fraction bits. So if I were to illustrate with an example, so consider a number which is like minus 2.74, and I want to convert it into a fixed point number with a word length of 6 and a fraction length of 3. Then the first step is scale it up by 2 to the power of your fraction length. You'll get this 21 point something. You discard this fraction and just retain the integer. And at step 2, based on your word length, so it's 6 bits. So if you will have to clip it if it doesn't fit into the range of 6-bit 2's complement number. That's it. So the two easy steps give you the final output. In this case, there is no clipping required because 21 itself is self-sufficient to be represented in 6-bit 2's complement. So you have represented minus 2.74 as an integer, which is 21, with an implicit scaling factor of 8. So that's how basically fixed point works. And yes, this process incurs a bit of a quantization loss if you convert back into the fraction because of this discarding. But by choosing the word length and fraction length appropriately, this can be kept to a minimum and almost has no impact on the network accuracy in most of the cases. So now we understood how the architecture looks, how the numeric format is dispatched onto it. Now the last piece of the puzzle is how does the Memristor device look? So that's what we can see here. So Memristor is basically a resistive storage of data. It can exist in various types of devices based on what physics is used for that resistance or conductance. In our work, we focus on resistive random access memory, which stores the data as conductance of an oxide layer. So it basically has an oxide layer, which is sandwiched between a top and a bottom electrode. Now, the oxide natively contains oxygen atoms, which are non-conductive. But if you apply certain programming stimulus to it, you can break the oxide down and create oxygen vacancies, which are conductive. So by creating or controlling the amount of vacancies created or making them depleted, you can achieve various conductance states, and each state corresponds to digital data, giving a single device multi-bit storage capacity. So far we have looked into all the fundamentals of SIM, the architecture, the number format, and the device, and also established that it's a good energy efficient alternative for edge AI. However, there is no free lunch, and these benefits come at the cost of a certain challenge. There exist quite a few challenges in SIM architectures. In this paper, we'll focus on one particular challenge and how that is addressed by the related works and how we can make things better for that. So to go into the specifics, the challenge we want to address is the conductance variation within the Memristor devices. So what is conductance variation? So the Memristor device is a very small and oxide-based device. So it has a stochastic physics and also has fabrication imperfections. Because of this, whenever you try to program a Memristor, its finally programmed value will be different from what you target. It won't be a point value, it will have a distribution around it. Now, if you look from a simple multiply accumulate operation point of view, that means each conductance has a delta with it. That means each current that the stimulus creates in it will have a delta with it. So accumulated current has a delta and your output has a delta, which is basically an error. And if you have a neural network, then these errors will keep propagating through the layers and finally degrade the final accuracy of the network. So the neural network functionality is basically affected adversely by conductance variation. Moving on to how related works have addressed the problem of conductance variation so far, we can group them into 4 categories based on the works that were existing at that time. So the first category is on-chip training. So you train the network directly on the chip itself so that it accounts for all the variation that is existing in the devices. However, this is not scalable because you have to do it on a per chip basis, and the Memristor programming is expensive in terms of energy and also has endurance issues. So it won't be scalable because of that as well. So alternatively, you can try to model the hardware into a software code and insert that code into your training process to get the trained weights which can tolerate the variation better. But again, you have to model each hardware separately, and that is also not a scalable idea. Moreover, this method focuses on tolerating the error, but doesn't focus on like reducing or mitigating the source of the error to begin with. A third approach is that you train in software, but before mapping your weights to the hardware, you first characterize the chip, figure out high variation memristors, and try to avoid mapping the big weights to those memristors. Again, this will require a per chip characterization, not scalable. And also, sometimes it is not possible to map a certain weight to a certain location. So it's very restrictive to maintain the accuracy. And the last thing is you don't do any of the three above, and you just put some hardware on the chip, which takes care of the variation. But of course, as it's a new component, it's going to have its own overheads in the hardware format. So in a nutshell, the related works which try to work on the conductance variation problem are not scalable. They focus on tolerance rather than error minimization and also incur hardware overheads. Our goal is to mitigate the conductance variation while not having any of these problems. And that's where the quantization approach comes into picture. So we'll start with just a brief overview of how the conventional quantization and the proposed quantization looks. I'll start with the conventional quantization. So the standard flow is you have your real valued inputs, the activations. You have your real valued weights. You first quantize them both to fixed point, deploy them on the computation in memory hardware, get your full precision output. And if you directly propagate the full precision output to the next layer, the bit sizes keep on prohibitively increasing through a network. And actually, they don't contribute much to the accuracy. So in standard practice, you'll apply a second level of quantization to reduce it to a lower precision before feeding to the next layer. Now, in this entire flow, in the standard method, there is no consideration of how this can be leveraged to mitigate the variation. So phase one completely ignores any impact of variation. And in phase two, they just discard the LSBs to reduce the bit sizes. But the variation induced errors are more in the higher order bits because they have a higher scaling factor during shift and add. So ultimately, you end up with a high output error, and that will degrade the accuracy. In our approach, we try to do some smart modifications at these two phases so that without any extra compensation or going through the lengthy training modifications, you can directly get a low output error. So in the phase one, we try to tune the output format in such a way that it automatically suppresses the impact of the error. Now, whatever error that is residual and remains after phase one will reach the full precision out. At this phase, in phase two, you selectively discard the bits in a different manner. You don't discard them based on bit position. You look at the information content and the bit position and make a better decision so that most of the error is eliminated while the most of the information is propagated. So ultimately, you have most of the information retained in the final output, but a very low amount of error that was caused by variation. Now, in the next couple of slides, we'll look at how the phase one works, how this phase two works, and how those two will be combined into a full algorithm. So starting with the phase one, the key idea that we use is if you somehow can tune out the fixed point format of your output, the higher the fraction length, the lesser is the impact of the error. So for an example, consider this simple system on the left. You have a crossbar, it produces some error currents. So we are assuming the ideal output currents or ideal digital outputs to be ideal plus delta. I have removed the ideal because the discussion is only about the errors. So you'll see deltas everywhere. So you'll get some error currents due to variation. These will lead to some error values in digital. These will undergo shift and add, and this will give you a final accumulated full digital error, delta D, full precision, FP. Now, if you assume it to be like an 8-bit value, let's say 91 in this case, and your output format is having 4 bits of fraction, you can see the numeric error, if you consider the radix point, if it is 5.69. But if you had 1 bit more extra, you basically halve the error. So if somehow you can tune this fraction length, it is automatically reducing the impact of error without doing any fancy training or any new hardware component. So that's the first thing. And now let's consider we chose 8,5, which was a better option in this case. But still, you have this 2.84 delta to deal with. This is what will be dealt with in the phase two. So we saw residual error existed after phase one, which was that 2.84. Now what we will do is we'll discard the bits which have a higher error, but don't have much of an information content. So accuracy remains the same, but the error is significantly reduced basically. And the key point here is that these need not always be the LSBs, which are insignificant, because higher order bits are sometimes just there for sign extension. So that is basically zero information, but they have a high scaling factor, so they also have high errors. We can see it in this example again. So again, the error we had 2.84 in the 8,5 format. And let's say my final target is 6,3 format. So I have to eliminate 2 bits from somewhere. If you eliminate the 2 LSBs, your error is marginally reduced, not that much of a change. But if the 2 MSBs are like ignored, then the change is a lot. Now, in this case, the MSBs won't affect the accuracy because we are talking about the delta. For the original ideal output, assume that both these positions are sign extensions. That way, you are keeping all the information, but just getting rid of most of the error. So we understood phase 1 and phase 2. Now, the thing is how to decide these various parameters, the fraction lengths and what number of higher order bits or lower order bits to remove in the final outcome. So for that, we'll propose an algorithm. I'll just give a short summary of the algorithm and the hardware design to implement it on chip. Both the aspects will be covered on this slide. So as an algorithm, we start with the constraints, which are basically what kind of an architecture you have, what are the bit sizes, what are the converter sizes, how the data is flowing, and so on and so forth. And you have a threshold of accuracy that, okay, at hardware, I want a minimum amount of accuracy of this and this level. So that will be application dependent constraints. Now we chose the fraction length of weights as the tunable independent variable because we have those equations in the paper. So you can derive all the other variables like the output fraction length or number of higher or lower order bits to discard in the quantization phase 2. All of this can be derived using this weight fraction length as an independent variable. So if you tune this, you basically end up with these values automatically. So by tuning this and going through a design space exploration phase, you figure out the weight fraction length, which gives you an optimal output fraction length that is giving you the highest suppression of the errors and also giving you how many bits to discard from the higher order and lower order bits. Now, once you have this data, you can implement this thing very easily in hardware because at phase 1, we were just tuning the fraction length of the outputs. And as the radix point is implicit in the fixed point format, there is no hardware modification. It's just a scaling factor, which now has a different value. For phase 2, there is a slight change because in the conventional way, you were just discarding a fixed number of LSBs, but now you have to configurably discard a few LSBs and few MSBs. So you need a selection logic, which can select a subset of the output bits given like a certain offset value. So it's very simple. It just requires like a couple of registers and a multiplexing logic. And since you can configure the offset in the register, you can adapt it to any workload post fabrication. Now, having understood the technique, how it works, how the configuration decisions are made, and how the hardware is designed, let's go to the result. So I'll first start with the simulation-based evaluation of our technique, and then just briefly show a chip prototype onto which we deployed the quantization based on this approach. So as for the setup, these are like the basic parameters. So in order to simulate the same hardware, we just assumed a baseline architecture like ICCAD. And the variation data was taken from Prakash, where they had fabricated devices on which they measured the variation. We had 8-bit weights and 2 bits memristor. So 1 weight fits into 4 memristors. As for benchmarks, we used AlexNet, VGG, and ResNet with SVHN, CIFAR 10, CIFAR 100 respectively. And these networks are a bit modified because they are originally intended for ImageNet. So you have to tune them for these different image sizes. And the workflow or the evaluation tool chain is that we trained the networks first in PyTorch, froze the weights, then tuned and performed the hardware inference using an in-house sim simulator. The quantization and the inference simulation, both of those were done in this value. And finally, we estimated the area, energy, etc., using results from ASIC synthesis for our technique, which was performed in Genus using TSMC 40 nanometer PDK. So the first result is the accuracy, which was the core point of the whole discussion. So here you see the accuracy trend for those 3 benchmarks, AlexNet, VGG, and ResNet. And the independent variable, which is the weight fixed point format, is plotted on the x-axis. So the bit size is basically same, 8 bits. We just want to tune the fraction length so that the hardware doesn't go significant changes. And if you see a fraction length greater than word length, that is not an anomaly, that is possible, because it just means that your fraction has a leading 0. So 8, 9 would mean that instead of 0.8 1, you'll have 0.01 all the time. The first digit after the decimal will be 0, and that will continue for rest of this. And the trend is pretty similar, where the red bar shows the fixed point or the quantized software accuracy, ideal accuracy, and the green bar shows the quantized hardware accuracy with the variation and all the stuff that is going on. So as you see, as we move from 6 to 9 in the fraction length, the accuracy increases. This is because the higher the word length of the, fraction length of the weights, the higher is the fraction length of the output. That means more suppression of the errors. So you see the matching progressively becomes better. And it peaks at 9 because when you go after 9, yes, the matching is still good because the error is getting suppressed. But now you're assigning more and more bits to the fraction part and the total bit size remains the same. The integer part has less bits devoted to it. So you are not able to represent the integer parts of the data flow values correctly, and that's why it keeps dipping. So you observe the same trend across all the 3 data sets. And in that way, we can see that by just tuning this simple variable called as a fraction length, you can basically go from this 10% accuracy at hardware to straight away at matching the quantized software accuracy. And what is the impact of that technique onto the hardware matrix like energy, area, and etc.? So as we see, we had significantly higher accuracy at an expense of slightly more energy and area because we need a simple modification for the truncation logic. But if you bunch all of this information together into a combined matrix that is correct operations per unit energy, then the proposed approach outperforms the state of the art significantly by about 5.66. And the overheads are quite low, as you can see here. And lastly, after developing that technique, we were also at the same time developing a chip prototype for a healthcare application where we were classifying the heart activity, the heart ECG heartbeats, into the abnormalities so that we can detect cardiovascular diseases earlier. So on this prototype, we actually, when we trained the final model, we quantized those weights using the aforementioned technique and fabricated it into a full chip. So this is how the entire system looks. So that's the PCB. This middle thing is our chip, which was part of a multi-project wafer. And we had an in-memory computing chip with resistive crossbar and digital processing, and some characterization circuits to obtain additional result about the analog periphery in 40 nanometer technology. It consumed about 2.9 square nanometer silicon area. And this is just a minor demonstration of the functionality where there is a control sequence in the output layer. When the control sequence of the FSM finishes, you get the prediction output, which is class number 1 in this case. So to conclude, computation in memory is a very attractive alternative for beyond von Neumann computing, targeting edge AI. But issues like conductance variation reduce the computational errors and thereby hamper the functionality. In our paper, we propose a quantization methodology which can overcome this in a very lightweight manner by tuning the output fraction length, which suppress the errors, and then again further reducing the residual error by selectively discarding MSB and LSB parts of the output. So, and ultimately leading to 5.6x correct operations per unit energy. And we also deployed it on an actual chip prototype targeted for a healthcare application. So thank you for your attention. And if you have any questions, I'll be happy to answer.
All right. Thank you very much, Sumit, for the nice presentation. Do we have any questions for Sumit? Surya, we cannot hear you. I think you're talking with.
Sorry, I can't hear you either.
Yeah, you can also type your question and I will read it.
Okay, do you hear me now?
Yes, we hear you now.
Okay. So my question is for deciding the number of the bits for the fraction. It depends on the workload, right? So if the workload changes, that changes too. So you need to always fine tune it for the specific workload.
Yes, but it's not an extensive process because once you fix your word length, then you pretty much have like half of the space to work with, half to 60% of the word length to work with. So the design space will be too small. And if you look at the quantized version of most of the models, you go somewhere between 8 to 16 bits, not beyond that, because then it's basically same as floating point. So the space is not that big to explore, and it's a linear search. There are no combinations. So it's very manageable in that aspect.
Yeah, all right. Thank you.
Yeah. Thank you.
Right. Any other questions?
So the recording is going on, right?
Oh yeah, sorry. We will
I just
have to-
realized.